All right, everybody, this is Miss Thompson. We are going to take notes today on identifying arithmetic, geometric, and quadratic sequences. This is for the purposes of Math 1, so we're going to focus mostly on arithmetic and geometric, but we will also learn a little bit about quadratic as well. So identifying arithmetic should be the first section of your notes. Remember, arithmetic sequences will always give linear functions because they add or subtract over and over. So what does a graph look like? Should be a straight line going up or a straight line going down. So what does the sequence look like? Well, over and over you're going to add, possibly, or you might also subtract over and over. Okay, so what does the explicit function look like? Is there more than one possible form? The answer to the is there more than one possible form is yes. Though we've only really talked about this one, where you fill this in right here with your common difference. You fill this in with your f of 0. We learned earlier this year that we can also have linear functions that are in standard form, ax plus by equals c, and point slope form, which was the y minus y1 equals m, which was the slope, times x minus x1. An easy way to identify these sequences is that they will never have an exponent. Not at all, unless it can be simplified through PEMDAS. So, for example, you could have y equals 3x minus 2 to the third power. That's supposed to be a little 3 right there, which would be the same thing as saying 3x minus 8, and that would still be considered a linear function once you have simplified that. So moving on to the next section, what does the recursive function look like? Well, we know that they all start like this. F of n equals f of n minus 1. And then we've got this blank right here that we fill in. And then we also have an f of 0 usually equals blank. And so then in here we would put our plus or minus something. And then here this would be your 0 term. Now, keeping in mind that you can also, right here, go and put in f of 1 equals something, or f of 2 equals something. You can have anything in there as long as it is recursive. Okay, so moving on to how do I identify it from a table? Check to see first if the table needs to be rearranged, or if it is missing any terms. These are going to make better sense in just a second because we're going to do examples of each. So if it needs either of those things, you're going to rearrange it. And then what you're going to look at is the pattern in the f of x portion of the table, which is usually the right in a vertical table or the bottom in a horizontal table. Okay, so looking at this first example, first thing that I see is it goes 0, then 1, then 2, then 3, then 4. So it's all in a wacky order. So first thing let's do is let's rearrange this. So we're going to have a 0, 1, 2, 3, 4. And then we're going to have -1 was with the 0, 4 was with the 1, 9 was with the 2, 14 here, and a 19 here. Then we're going to follow the instructions of, let's look at the f of x to see what's happening. So here we have a plus 5, plus 5, plus 5, plus 5. Make sure to check every single of the plus 5, plus 5, plus 5, plus 5. Do not just assume that because the first one is a plus 5 that the rest of them will be. So because it's adding, it is linear or arithmetic. Oh, guess I can't fill in that letter there. So the common difference here is plus 5. Let's try to get that. Yep, there we go. That I back in there. Okay, moving on to the next one. So looking at this one, I see that right here, I should have a 1. Right here, I should have a 3. And right here, I should have a 5. So we also need to remake this table, so to speak, and add those in before we can start looking for a pattern. So 0, 1, 2, 3, 4, 5, 6. So we had a 15. I'm going to scratch that out. 15, and a 9, and a 3, and a -3. So this is where we kind of do the daddy frog, baby frogs thing a little bit. We say that from here to here, we went down by 6. So what that means is that from here to here, it must be -3 and -3. So this right here would end up being 12. And if I keep subtracting 3 over and over, I get 6 right here and 0 right here. Now we can go through and look for our pattern in the f of n column like the note said. So here, or actually we've already identified the pattern by filling in the blanks because we have a -3 and it's a -3 over and over. So -3 is my common difference and this means it must be linear. Now keep in mind you're going to be given one representation, for example, this table, and you're going to have to determine if it's linear, exponential, or neither, or quadratic, which we'll talk about in a second. So looking at this table, if you have this -3, that means that it's going to be linear is going to be your choice. Okay, identifying geometric. Remember that geometric sequences will always give exponential functions, graphs, and tables because they multiply or divide over and over. So what does the graph look like? Well, we have the graph that goes like this, which is multiplying, or the graph that looks like this, which is dividing, or, come on, make my dot, or multiplying by 1 over something. So what does the sequence look like? We would have times something, times something, times something, or we might have the divided by something, come on marks, and then the divided by something, etc. Okay, so what does the explicit function look like? Is there more than one way to write it? For this one, there really is only one way. So we have f of n equals I times m, and then we have this little bitty raised up n right here. It's smaller and it's raised up. Now, sometimes you will see I stands for initial, and sometimes you'll see B for beginning. In that space, depends on the teacher that you've got. So geometric sequences, the easy identification is that they will always have an exponent of x or n or any variable. And it looks like the any did not. So let's, okay, or any variable. Usually our most common ones are the x here or the n here, but it depends on if you have a story. Okay, recursive function, very much the same as your recursive function for an arithmetic or linear. F of x equals f of n, f of n equals f of n minus 1, fill in that blank, and then usually with the f of 0 equals something. And in here, we always have times some amount, where this is going to be greater than 1 if it is increasing, less than 1 if it is decreasing. And then again, you could also have f of 1 equals, f of 2 equals, or really f of 100 equals right there. Okay, identifying it from a table. Still similar in that we need to check to see if the table needs to be rearranged. Yep, that one didn't want to write. Or is missing any terms. If so, fix these issues. Then we are going to look at the pattern of the f of x, f of n, which is the number of tiles, for example, that a term might have in a sequence. So here, seeing that we go 0, 1, 2, 3, 4, again, similarly, to the arithmetic one, we are going to recreate this table in order. 0, 1, 2, 3, 4, and we had a 3, 12, 48, and 192, and 768. So now let's look at how is it changing. Well, it's getting bigger. So that is greater than 1, greater than or equal to 1. And so we have a times 4 here and a times 4 here. So double check, but that should be times 4 over and over if I did my math ahead of time correctly. So common ratio of times 4, and because it is multiplying, we can say geometric or exponential. Okay, next table. So here, looks like we're missing some terms here. So let's look. So right here, we need a 1. Right here, we need a 3. And then we have a 4 or 5 here that goes in order. So let's go ahead and add some space in our table, just in case it's helpful. With that 4 to 5, we might not need to. 0, 1, 2, 3, 4, and 5. So we had the 1/3, and we had a 9, and an 81, and a 243. So let's try to use the 81 to 243 and see if we can figure out what's going on. So I see 8 and 24, and 8 times 3 equals 24. So I think this is probably going to be a times 3. So let's check it. 9 times 3 right here would be 27, and then 27 times 3 is 81. So yep, my common ratio is a times 3. So then to get the 1, if I wanted to or needed to, I could then go backwards by dividing by 3, and I would have a 3. So times 3 is definitely exponential. And geometric. Oh, I had a little spelling issue there. All right, so now quadratic. This is a new one for most of you, I think. So let's take a look at quadratic graphs. So what do graphs of quadratics look like? So this would be a positive or increasing. This would be a negative or decreasing quadratic. So now the sequences on this one, we actually have to look at a first difference, and then we have to actually take a look at the second difference here. So here, for the first difference, it's going to look like there is no pattern. Or what you're going to see is that the pattern goes like, for example, +3, +5, +7, +9. And so you can see that that's like it's adding an odd number, but it's not adding the same amount over and over and over again. But if we go here, we can see that the second difference from the 3 to the 5 is a +2, 5 to 7 is +2, and 7 to 9 is +2. So the fact that we have this common second difference means that it is a quadratic. Common second difference. All right, so what does the explicit function look like? Is there more than one possible form? So I'm going to write some different forms down here for you guys, and you're going to experience these more in Math 2 next year. So factored form is going to look like f of x equals x minus h, and then parenthesis x minus k. And so two sets of parentheses where you are multiplying in between. Standard form is f of x equals ax squared plus bx plus c. And vertex form looks like f of x equals a parenthesis x minus h parenthesis squared plus k. This is actually very similar to, let's erase right there. Similar to point slope in my linear functions. Oops, missing an E on there. Okay, so quadratic functions, and I put this in here and just realized that I'll have to explain part of it. Quadratic functions will almost always have an exponent of 2 attached to a variable. So you can see it right here. You've got an exponent of 2 that's basically attached to this x right here. And you've got an exponent of 2 that's attached to this x right here. Now, where this one is missing, or seems to be missing, come on, marker, catch up with me. The squared is because it is in factored form. What you will learn is that if you FOIL this, is how some teachers teach it, or if you double distribute, here the x times x is x squared. So you will still see the squared term right there, that exponent. So what does the recursive function look like? I'm just going to give you what it looks like, but we're not going to talk about it too much. So f of n equals f of n minus 1, just like usual. And just like usual, you're going to have a starting point. But then what actually goes in here is an mx plus b. You'll learn more about that in Math 2. All right, so identifying it from a table, you will be expected to do in Math 1. So first thing, check to see if the table needs to be rearranged. Same as before. Or is missing any, come on, ing, any terms. If so, fix these issues. Then we're still going to look at the pattern of the f of x, or f of n. Only this time, remember, we have an arithmetic, it adds or subtracts, second difference. So looking at this one, to make it easy, because this is Math 1, I'd put these ones in order. So you're not going to have to do any rearranging, at least in Math 1, for this one. But now let's look at the first difference. So right here, plus 2. Let's erase, make that a little more clear. Plus 2. Here we have a plus 4. Here we have a plus 6. And here we have a plus 8. So that's my first difference. Sorry for the sloppy handwriting. So then looking at the second difference, here I have a plus 2, plus 2, plus 2. So, yep, quadratic. Common second difference, plus 2. Okay, so lastly, if the sequence that you're given doesn't match any of the sequences discussed in these notes, then your answer is neither. All right, enjoy, guys. Thanks for listening.